Hello, everyone. Welcome to the session on use of machine learning in internal models for risk capital. Now, before we dive into the topic, let's face it. I mean, machine learning is something that is growing at unprecedented speed today. We are all witness to the rapid growth and adoption of machine learning in all phases of the game, and yeah, it is not something that is unknown. Everybody is aware about it. Everybody has started using it. Individuals, organizations, everybody is using machine learning in some form or the other. Knowingly, unknowingly, we are all using machine learning. Okay. And yeah, so this session is about how machine learning is being used or is expected to be used in internal models for risk capital. So as we know that we have pillar 1 and pillar 2 for different risks under which we have to come up with capital calculation. At the end of the day, if you look at the exercise, we are coming up with we are predicting loss, correct? And whether you directly predict loss as a figure, or you predict it using some kind of microstructure, such as model different components like PD, LGD, EAD, and then using those components together, you come up with capital. At the end of the day, it is a prediction exercise, right? Whether you are modeling, PD would be a classification exercise because it's a probability that you are measuring for default versus non-default. If you're measuring LGD, that's a regression exercise. So in all of these capital calculation, if you're looking at, we're trying to predict a loss figure, right? Whenever prediction comes to the picture, machine learning gets involved because that is what we do in machine learning, right? So we have a class of supervised learning where the task is to predict. There are other types of machine learning, but primarily we are interested in prediction, right? So banks have started using machine learning in some capacity. And obviously, regulators cannot keep silent. They have come up with some guidelines. Nothing too prescriptive, but mostly like principle based guidelines. Like these are the principles that you need to follow when you think of using machine learning, right? Yeah, so in this session we will do a quick review of the guidelines. Yeah, it's a short webinar, nothing too concrete, but it is all principle based. So we'll go through those guidelines, and then we'll discuss what that means for us. We being the risk professionals, what does it mean for us? Okay, where are we heading? What should be the next steps? How should we prepare ourselves? So that's sort of the agenda for today's session. So let's proceed. Quickly, I'll just go through the topics that we'll cover. So we'll briefly touch upon the regulatory updates that we have in this particular space. And then we'll distinguish between the classical econometrics versus machine learning models. This distinction is important because a lot of these guidelines are based on off of this taxonomy. What qualifies as a classical econometrics or traditional approach versus machine learning approach? And if you look at the regulations, they are primarily targeting IRB. Okay, so when we talk about internal models, right? What do we mean by internal models? You know that in every risk there are primarily two flavors. There is a standardized approach and there is a advanced approach. Advanced approaches are called as internal models. So we have IRB in credit risk, we have IMA in market risk, IMM in counterparty credit risk, right? So we have internal models or advanced models in all types of risk. The papers primarily target IRB, but the latest guidelines also say that wherever it is applicable, it is extendable for counterparty credit risk, market risk, and even CVA. Okay, wherever there is a prediction, whether you are predicting a default probability or let's say an exposure, right? That will follow these guidelines. Okay, so we'll look at the challenges in credit risk. We'll also look at the current adoption of ML. So there was a survey that was floated by EBA A lot of questions were asked to different banks in what capacity the banks are using ML in the IRB space. So they have all responded. So we'll review what is the current adoption of ML in IRB. What are the challenges and benefits of ML models? And then what is the prudent use of ML models going forward? So this is the final recommendation. Again, as I said, there is nothing concrete. It is all principle based recommendation. So we'll review that. And then finally, we'll wrap it up by discussing on what it means for us. Okay. So that's sort of the agenda for today. All right. So there have been a lot of influx of different types of papers. If you look at Bank of England publication, BIS, FRB, EBA, right, BCBS, a lot of papers are there. I have picked a few which are very relevant. So I would urge you to go through these papers at your convenience. Okay, so a lot of good thought-provoking things are there. It is important for you to understand the current landscape and yeah, and basically understand where the regulators are coming from, and make sure that you understand all these arguments. If not, then we have a lot of catching up to do, right? Yeah, so you can take a look at this paper, Bank of England discussion paper, Artificial Intelligence and Machine Learning, October 2022. BCBS has also released a couple of papers, machine learning applications in central banking, regulating AI in the financial sector, recent developments and main challenges, December 2024. Primarily for this session, I have focused on the EBA papers. Okay. So the first discussion paper came in November 2021. I can share the link to this document or you can find it. It is easy to find. Just go through this paper once. Okay. And in this paper, there are a lot of questions asked to banks. In what capacity are you using machine learning today? So they have all responded. So a follow-up report came in August 2023 that kind of summarizes the response, right? And finally, very recently, July 2025, ECB published a revised guidelines for the internal models, and they have a specific section for use of machine learning. Let me actually show you that paper just quickly. Right. So this is the paper that I'm talking about. This came in July 2025, so very recent. And in this guidelines, they have put a specific section, section number 9, the use of machine learning techniques in internal models. It is not long, so I would say just go through this once. Yeah, and this session is primarily based on the whatever guidelines have been prescribed here. Okay. So yeah, when you get some time, I would strongly urge you to go through these papers. All right, let's proceed. Okay. So now let's talk about when we say models, there are two types of models: classical econometrics models, or they are, as EBA calls it, the traditional approach. And then we have this steroid infested machine learning models, right? Let's understand the distinction. That is important. Okay. All right. So here's the distinction. I have listed a few factors that are different between these two class of models. When we talk about econometrics models, so you can think of this for the time being as simple linear regression. Okay, simple linear regression, we all know that is the heart of econometrics. Okay, and machine learning models, you can think of, there are 50, 60, 100, I don't know how many models are exist today. I mean, it's growing at a speed nobody is able to catch up. So yeah, I have listed a few important class of models here, but it's just growing day by day. Okay. All right. So let's understand what is the objective of econometrics models. See, econometrics models are grounded in probability and statistical theory, right? When we talk about linear regression, you get a lot of output, even in Excel, or if you go to Python, use stats models, you'll get a lot of statistics. R square, adjusted R square, T stat, P value, F stat, right? Lot of statistical results are there, and we have a lot of hypothesis testing that goes in terms of estimating the significance of different parameters. So the goal of econometrics is really to do causal inference and hypothesis testing. Causal inference means if does X explain Y, okay, cause effect relationship, and a lot of hypothesis testing. So this is where econometrics really shines. But coming to machine learning, nobody talks about statistical assumptions, distributions. There is some element of probability, of course, but it's not as rigorous as we have in econometrics. In machine learning, our primary focus is on accuracy or prediction quality. Okay, how accurate you are in your prediction. And generalization, that's a big topic. So, in short, I'll tell you what generalization means. Generalization means the ability of the model to perform well in unseen data. That means where on the so we have two types of data or like three sets of data. Training set where the model is trained. Then we have a validation set where we tune some of the hyperparameters. I will explain what hyperparameters is a little bit later. And then we have a testing set which is completely hidden away from the model until the end. So once the model is trained and tuned, then we test the performance of the model in the test set. Good generalization means the model should be performing equally in all kinds of data, training set as well as test set. If it performs brilliantly on the training data that it has seen, but performs horribly on unseen data, live data or test data that is not seen by the model, then we say it has very poor generalization. Okay, so that's in short what generalization means. The objective is the machine learning to be able to predict in all kinds of data, right? Not just the training data, but whatever is not seen yet. Ultimately, these models will go into production and will be used for live forecasting, correct? So it should be able to perform well. So that's the goal of machine learning: quality, accuracy of prediction, and generalization. Assumptions. In econometrics, we have a lot of strong assumptions. If you remember, it's in simple linear regression. For OLS estimation, how many assumptions are there, right? Linearity, exogeneity, homoscedasticity, no perfect multicollinearity, all these things are there. In machine learning, we don't care a lot about assumptions. Okay, so they kind of take a backseat. Weak assumptions, flexible assumptions. Interpretability, this is the big topic. Okay, econometrics models are highly interpretable. Think of simple linear regression. Two parameters, right? Beta 0, beta 1. Beta 0 is the intercept, beta 1 is the slope. Each coefficient is highly meaningful. We exactly know what the model is doing, right? So there is high degree of interpretability. When it comes to machine learning, this is where machine learning really suffers, and that's the main problem area. It is kind of like a black box. Some of these state of the art machine learning that we use today, algorithms, are kind of black box in nature. It's very hard to interpret. So, for example, look at deep neural network. With so many neurons, hidden layers, one thing transforms to another using nonlinear activation functions. And from the time you go from input all the way till output, you have lost track of what's going on inside, right? So, machine learning models are black box in nature, and that leads to low interpretability. This is the one that causes challenges in terms of adoption in regulatory capital calculation. Okay, we'll talk more about this. Coming to data, right? Data handling capacity of econometrics models is small. And here is the important thing: econometrics models or traditional or classical models are theory driven. And we assume there is a DGP. DGP is data generating process. Okay. So the actual process that generates the data, Y and X, that's DGP. We speculate a model how the world works. That comes from us. Okay. For example, CAPM model, capital asset pricing model. Excess asset return is a linear function of, let's say, market premium. That's the theory, right? All kinds of econometrics models come from a theoretical underpinning of, or the economic rationale that dictates the structure of the model. Okay, a human being comes up with the model specification. It's theory driven. But if you look at machine learning, data handling capacity is large, large high dimensional data. You can have millions of different X or features, right? If you have those many features in econometrics, we'll simply struggle with ensuring all the assumptions are being met. A lot of assumptions are there. But in machine learning, yeah, data handling capacity is large, but more importantly, it is not theory driven. Nobody imposes a structure in the beginning. This is where we let the data do the talking. Let the data come up with the specification, whatever is the best, right? We don't impose structure on machine learning algorithms, right? So that's the fundamental difference. Okay, coming to parameters. How many parameters are involved? In econometrics models, we have a very few parameters. In fact, I don't know if you have noticed, look at the name. It has to do with economy, right? Economy means it's not the economy as in macroeconomics. Now, I'm not talking about that. How economically you can explain the relationship between y and x. Okay, by definition, we have to deal with parsimonious set of variables, only a few variables. Can you explain y versus x using 2 or 3 variables? That is what econometrics is all about. Number of parameters is small. Look at simple linear regression, only 2 parameters, right? Slope and intercept. If you look at machine learning, the number of parameters simply blows out of proportion. Um, Let me ask you a question. What do you think is the number of parameters used in ChatGPT 4? Just take a guess, right in the chat. Any rough estimate of how many parameters are there in ChatGPT 4 that get trained? Take a guess. 10 lakhs, 1 million, 1 billion. Okay. Don't ask ChatGPT, hey, how many parameters are you trained on? 5 billion? Okay. It's one ChatGPT 4. ChatGPT 4 has 1.76 trillion parameters. Trillion. Now all of these make sense, right? How do you infer that model? It's obviously a black box. That many parameters we are using. Why are we using this kind of thing? Short answer is because we can. Because we can. Today we can. Why? We have the data and we have the computing power. So why not? Because we can, right? Main difference between parameters. Obviously, when you have 1.76 trillion parameters, how do you interpret the role of those parameters? Next, big data. So when we say big data, I mean, there are multiple definitions to it, but primarily I'm talking about unstructured data. Unstructured data means data that is not in terms of rows or columns. So think of text, audio, video, different JSON files, emails, all kinds of things. Machine learning models are capable of accommodating unstructured data. Okay, but econometrics models are not. And finally, this is one dimension that regulators have talked about: non-linearity. So in econometrics, handling non-linear relationship is limited. I mean, we have to impose the structure. If you want to use a quadratic regression, you can. If you want to use an interaction term, you can. Handling non-linearity is limited, but when it comes to machine learning, automatically non-linearity is handled through the multiple layers of transformation in deep neural network architecture. And with higher number of neurons and hidden layers, we can achieve any kind of non-linearity. There is, in fact, a theorem called a universal approximation theorem, which states that deep learning models can be used to approximate any function, any kind of function. The output would match the whatever transcendental function you have. It can match by increasing number of neurons and hidden layers. Okay, so yeah, this is one dimension which is different between these two. Regulators have talked about all of these. So the boundary between econometrics models and machine learning models is little blurred at the moment. But these are some of the principles that you can, use to distinguish between in the spectrum. Where does this lie? Is it more econometrics than machine learning, or vice versa? All right. So these are some of the distinctions that you need to keep in mind. And here is a diagram that gives you the trade-off between model accuracy versus interpretability. Standard rule of thumb: more accurate the model is, you will lose on interpretability. So starting with this, right? Rule-based learning. Rule-based learning is the most simple type of algorithm, which is based on, let's say, heuristics. For example, if loan to value ratio is more than 80%, then do this. If it is less than 80%, do that. That's a rule-based learning. It's highly interpretable, but accuracy would be low. Okay. Then we have linear and logistic regression. Sorry for this typo. This is the classical econometrics model. Okay, lot of statistical interpretation and interpretability is there, and adoption of this today is massive in all kinds of capital calculation, stress testing. Also, we use pretty much linear regression after transforming the variables to do forecast. Correct. Decision trees. A single decision tree, just one tree, is still considered as part of, not machine learning. It is interpretable. I think this is where the boundary lies. So when you go to k nearest neighbor, additive models, support vector machines, ensemble learning, which has to do with, bagging, boosting, XGBoost, random forest, all those algorithms, and finally deep learning, which is deep neural network. I think from here all the way, this is all machine learning models. Okay. And you lose interpretability, but the accuracy keeps improving. So just remember this trade off. All right. Let's proceed. So, what are the main challenges when we want to use machine learning for credit risk calculation? When I say credit risk calculation, I'm specifically talking about IRB, okay, capital models. Now, here's the thing: banks are already using machine learning models. They're not new when it comes to credit approval process, which is decision making process. Should I give the loan or not to the particular obligor? We are using a lot of machine learning techniques today. That is there, but their adoption in IRB is minimal, and it poses these challenges. We'll talk about that primarily because of the black box nature of machine learning algorithms. Right? You don't know what's going on inside. It's so complicated with so many parameters. It's a black box. It's not humanly understandable. So these are the major challenges in terms of adoption of machine learning in IRB. First one is interpreting the results. Right? You give some input to the let's say deep neural network. It gives you some output. How do you infer which features translated to that prediction or probability? How do I interpret these parameters? So interpreting the results is a big challenge. Second, important, adequate understanding by management functions. Does everyone in the bank understand machine learning? We need to have the skill and expertise um, to understand these algorithms, how to interpret those results, understand strengths, limitations, assumptions. So training of the staff is essential. Today, not everybody understands machine learning. It's obviously highly mathematical and rigorous, so it's not everybody's cup of tea. So if you want to embrace machine learning, this is another major challenge. Okay. And finally, you obviously have to satisfy the supervisor, right? Justify the results to the supervisor. Because of the black box nature, it becomes hard to satisfy or convince the supervisor. So these are some of the practical challenges in terms of adoption of machine learning in credit risk modeling. Now let's take a deeper dive and understand what are the challenges and benefits of machine learning. Okay. So think of from an IRB perspective, the latest regulation has increased the, or extended this framework to be applicable for other risks like market risk, CVA, things like that. But primarily, the arguments are all given in the context of IRB. So we'll focus on that. I think now will start coming. Okay, a lot of these guidelines will start coming because machine learning is something you cannot escape today. I mean, it used to be a very nice thing to have earlier, maybe 10 years ago. Today, it's just you cannot escape. So eventually, we'll end up adopting it in some way or the other with a lot of protocols and monitoring tools in place. So that is where we are headed, and I'm anticipating a lot of new regulations will come. How much it will be principle based versus how much will it will be prescriptive, that we have to see. But this is a reality. Let's face it. It is machine learning is a reality. It is not a theoretical exercise. It exists, and it's deeply entrenched in our system, and it is growing every day. Right? We'll all agree to that. Okay. Coming back to challenges and benefits. So first and foremost, let's talk about challenges. Under risk differentiation, um, the definition, and so in differentiation, okay, there is a question: does IFRS 9 allow ML models? So here's the thing: right now there is no clear cut. This is the moral of the story. Nobody is saying don't use machine learning models. It is all principle based. You can use whatever you want, but it should have certain principles that needs to be satisfied. We'll talk about that at the end. Okay, almost there. There is no strict guidelines in terms of what you cannot use. It needs to follow certain or satisfy certain criteria for it to be approved, and those are all principle based. Okay, that is the stance of regulators today. So we'll go through that. Coming to risk differentiation. So in this space, what are the challenges? Definition and assignment criteria to the grades or pools. So you come up with a assignment rule, right? This is how I assign this obligor to rating C or this particular pool. There is a criteria, right? And that criteria will come from either logistic regression, decision tree, whatever you have. When it comes to machine learning models, there is no clear economic link between the input and the output because it has gone through several stages of nonlinear transformation, and we do not postulate an economic theory that probability of default would increase or decrease based on certain characteristics. We let the data decide, right? In machine learning models, we let the data do the talking. So we do not impose economic rationale, okay, between the input and the output. That is a problem. Now, complementing human judgment. So human judgment is also necessary whenever you have a model. First, it has to be interpretable. Second, human beings need to have override capability if need be, right? We call that overlay. Sometimes if the output is not accurate, then you can override those predictions, but you have to give strong justification why this is necessary. But when it comes to machine learning models, it is so hard to interpret and understand. Human beings are not able to play a role in interpreting the results or even doing overrides. We also use a lot of hyperparameters in machine learning, which are driven off of expert judgment. Okay. And this is also very hard when it comes to machine learning. I'll tell you what is a parameter versus a hyperparameter. Think of linear regression. Intercept and slope are parameters because those are learned from the data. Okay. But things like why simple linear regression, why not quadratic, why not cubic regression, degree of the polynomial, That is a hyperparameter. It is not learned on the data. It comes from expert judgment, or human beings impose that from outside. Okay, we don't learn those from the data. Similarly, if you come to machine learnings, there are a lot of hyperparameters. For example, if you look at, let's say, even in decision tree, I can tell you till what depth you want to uh, build that tree. Okay, 2 layers, 3 layers, how many samples you want in each of the final nodes, minimum number of samples. Those become hyperparameters. Okay, and in let's say deep neural network, what kind of optimizer you want to use, what kind of activation function you want to use, those are all hyperparameters. So any kind of I should not use parameter. Parameters are learned on the data by minimizing a loss function, but hyperparameters are supplied from outside using expert judgment. So there is a challenge in machine learning also. What kind of hyperparameters you want to set? Okay. Documentation, again, it's very hard because we don't understand the model. Hard to articulate the assumptions, limitations, and clear theory behind, that drives this particular model. We have to document everything to satisfy the supervisor, but this is challenging, right? So this is risk quantification. This is where we model the different components: PD, LGD, EAD. Now, sometimes, okay, yeah. So when we come up with the model, it should be intuitive and plausible. All the different links between Y versus X, and even the PD values for different categories should be intuitive. So, for example, if LTV ratio increases, right, loan to value, then PD should increase if you are using LTV for loss estimation. Things like that, right? So, but ML models sometimes give non-intuitive estimates also because they use such complex transformation of variables. It is possible for them to give non-intuitive estimates. Now the question is, do we rely on that? Okay, so that is the challenge. Number two is machine learning models use unstructured data, big data, as I told, text, video, audio, all those things. And here's the thing, the regulation says that you need at least 5 years of data to build PD, LGD models, correct? It is challenging to get 5 years of unstructured data for that particular obligor, right? So that is another violation or limitation, you can say, in terms of adoption of ML for quantification purpose. Let's talk about validation, model validation. So you have quantified the risk and everything, your models are ready. Now we want to validate that model. Resolution of validation failure. So whenever there is a departure, um, right, in credit risk or in market risk also, when let's say we exceed the value at risk, you have to explain why that breach happened, correct? What is the rationale behind this? It is very hard to pinpoint that failure when you are using machine learning models. Again, all of these challenges come from that simple statement that it is black box. Okay, so it poses a challenge in model validation. Also, the validation standards. It is very easy to create a checklist for econometrics based models in terms of testing the assumptions, test normality, text exogeneity. We have statistical tests, lot of statistical tests for time series analysis to all do all those things. But when it comes to machine learning, we have to come up with complex validation standards. It's not cakewalk anymore. The validation becomes even more engaging and involving. Okay. Special emphasis on out of sample and out of time validations. Machine learning models have a tendency to overfit. Overfitting is a huge problem in machine learning. Why? Because we have so many parameters, right? If you start just training and training and training on the same data, it will fit 100% on that data. And that is where the danger comes, overfitting. Because if you start overfitting on training data, you'll perform horribly on the testing data. That is the real purpose of machine learning, right? We want to predict in unknown, unseen data, new data. So there is in validation, we do a out of sample and out of time validations, correct? So these are not used in developing the model. We test the accuracy of the model in held out sample. Out of time means, let's say you train the PD model from 2008 to 2013. Out of time validation would be how does that work maybe in the year following years, 2014, 15, 16. Special emphasis on this because machine learning models tend to overfit. So we have to double down on these validations. So these are some of the challenges, okay, in terms of adoption of machine learning. What are the benefits? Again, the benefits come from better accuracy. Okay, so let's go through this. Again, same dimensions. Risk differentiation improves discriminatory power. Because you can use so many variables, so many different types of features and data, right? We are in a better position in terms of identifying all the relevant risk drivers, optimal segmentation across sectors. So you can have much more granular definition across jurisdictions, geographies, products, and come up with sectors, come up with segments or grades. So it really helps in improving the discriminatory power between the PD bands, right? You can have much more granular segmentation because it can handle so many features and it has good predictive power. That's why we can use it. Question from Sharabni. We can do hyperparameter tuning in ML models as well. Yeah, of course. The validation set is just used just for that. All ML models go through validation phase where we tune the hyperparameters. Okay. Risk quantification. Uh, so here we are talking about the actual prediction, PD, LGD, exposure. Higher predictive power, that means you'll get an accurate estimation provided you address the overfitting issue. Okay. But definitely at any day, the machine learning models will definitely dominate the econometric models if you're talking about raw predictive power. No doubt about this. Identification of unknown patterns, pattern recognition. See, here's one of the drawbacks. In econometric models, the model comes from a theory. A human being, based on his expert judgment and experience, comes up with this model. Hey, these are the potential risk drivers. Use those. Start with a linear model. If there are non-linearities, we'll see. And then with trial and error and a lot of iterations, that model evolves. That is how it works. But in machine learning, it can uncover patterns that even human beings cannot even perceive. Right? So definitely it helps there. In validation also, it helps in other aspects. For example, here's the thing. The challenge is to create a validation routine for machine learning models because it is so complex. Your number of checks and tests would be huge. But at the same time, machine learning models can also also help in data preparation step in terms of doing data quality checks, all automated. Okay. Missing value imputation, another example. When you are using missing imputation techniques for missing values, standard techniques is mean imputation, median imputation. You can also do regression based imputation, but when it comes to machine learning, we can use all kinds of things. We can use random forest or KNN for missing value imputation. These are popular. And assist in preparation of model validation reports. So generative AI, generative AI is being used today to create the first draft of model validation reports or even check your report. It is even capable of, if you just give the code, generative AI can create a model validation report compliant with SR 11.7. And then you take it from there. Okay, from the code, it can create the model validation report, generative AIs. Right? It can also flag issues with your code that it is violating these checks. That is where it has come today. So, yep. So these are some of the benefits and challenges of machine learning models. Okay, let's proceed. Couple of more slides and then we will open it for question answer. So here is the current landscape of ML adoption. when it comes to credit risk. So when I told you that EBA did a survey and it floated a lot of questions to the banks and banks have responded, and this is the summary. Today, banks are using machine learning primarily in lending decision and loan pricing space, as well as credit monitoring and recovery. Okay, so these are the areas where machine learning is sort of mature, I would say. But when it comes to regulatory capital calculation, these three areas: loan provisioning, so ECL, risk capital, pillar one, and stress testing, pillar two. These areas, the machine learning has not made its way yet. And there are challenges, obviously, in terms of regulatory approval, right? As we discussed. And this gives you a perspective of specific examples where this is used. So in model validation space, banks are using ML models as a challenger model. Okay, you know champion challenger model. So champion is the one that is in production, which is the best, and then continuously keep working on another challenger model. So ML based models are serving as challenger models to the champion model. Data improvements, machine learning models are being used for enhance your exploratory data analysis. A lot of different types of patterns, correlations, plots come up in when you use machine learning algorithms. Missing value treatments, as I mentioned, right? Data quality checks and missing value imputation strategies you can use using machine learning algorithms. For example, random forest, very popular. Variable selection, feature selection, very important, right? Where you have a lot of features, but you don't want to use all of them. So you want to use a few set of variables which are the most relevant. Machine learning models help you in that exercise. There are a lot of feature selection is a whole different topic. Lot of different methods are there. There are filter methods, there are wrapper methods, and embedded methods. Okay. Filter method is very simple. It's like checking t statistics or p value, whichever variable is important, take those, or correlations. We have wrapper methods, which are specific machine learning techniques that come up with that help you with the variable selection. For example, you can use ridge regression, lasso regression, elastic net regression. All those naturally show you what all variables are relevant. Okay, so machine learning techniques are used for variable selection also. One example for wrapper method is stepwise regression. We have forward selection, backward selection that helps you come up with a few set of important variables. Okay, the ridge lasso regression, all those that I mentioned as part of embedded, because it is a regression, but as part of that exercise, it does variable selection also. So that's why it is embedded. And in risk differentiation space, directly we are not using, so IRB PD is not being calculated using machine learning methods. Okay. However, they are using the raw PD estimates to fine tune those by using text mining. So you use traditional approach to calculate PD, but then you adjust those PDs using text mining. There is a lot of textual data that that comes from the obligor, so, and which are real time, by the way. So you use text mining to update those PDs. So that is being done today. So this is where we stand. Okay, this is the current ML adoption pattern across banks. Obviously, the next step is, what is the recommendation? Given the current landscape, given the challenges and benefits, what is the recommendation from regulators? Prudent use of ML. So, primarily, it revolves around these moral values. Okay, when it comes to ML, we have to be cognizant about these dimensions: ethics, explainability, interpretability, traceability. Traceability means if there is something, some failure happens, can we trace it back to the root cause? Okay. And auditability should be auditable, fairness, data governance, and protection. So it revolves around these moral values. Okay. Now, so this is a very brief summary of what is the final recommendation from EBA. This is based on the latest July 25 paper. So I'll just go through this. The number one recommendation is top of the list, adequate skill and expertise of the management staff. If you want to use ML, all three lines of defense should have sufficient knowledge of ML. Okay. Sorry, there is a question from Sarda. Are ridge regression, lasso regression considered ML? I would say yes, because they use a regularization term. We never use regularization term in traditional econometrics. Wherever you use regularization term, that is used to address the issue of bias and variance trade-off. Okay. Yeah. So since they use regularization term, I would classify them as ML. Yeah. Good question. All right, please understand this is the top recommendation coming from the regulators. First and foremost requirement is adequate skill and expertise. All three lines of defense should have sufficient knowledge of ML. Okay, your model development validation team, risk control unit, and the audit function. Everybody has to understand ML. Otherwise, it will not float. Okay. Number two, balance complexity and interpretability. So it is saying, as a rule of thumb, try to use conventional data as much as possible instead of unstructured data. Okay, just because you can use unstructured data doesn't mean you have to. If the performance is similar, on conventional data versus unstructured data, then go with this because this is more interpretable than using audio, video, all these things, right? Avoid excessive number of features. Do not, again, just because you can doesn't make sense that you should have 100 different features. So always shoot for parsimonious, right? So it is trying to blend these two ideas together, ML plus econometrics, right? Analyze marginal contribution of risk drivers. This is very important. So what they are saying is statistical analysis is still important. Even if you come up with a machine learning algorithm, figure out a way to explain which risk driver is contributing to the output in what way. What is the sign? What is the magnitude? This is also called as ceteris paribus analysis, which is you basically try to see the effect of one input on the output, keeping all the effects of other inputs constant. Okay, all else remaining the same, what is the impact of this X to the Y? So you have to come up with a way to assess the marginal contribution of risk drivers to the output. There are tools to do that. So we have a different branch of machine learning called as XAI, Explainable Artificial Intelligence. So here there is something called, we have something called as LIME and SHAP, which are used to unbox the black box nature of machine learning. So you use a machine learning which is black box, for example, deep neural network or XGBoost or something. Then we use SHAP or LIME to explain how it is actually using those input variables to perform that prediction. I have a Python example. Let me quickly flash that so it gives you a better concept. Yeah. So, for example, in this particular example, I'm using XGBoost. Okay, it's a credit, default probability of default modeling exercise. Using these attributes, I'm trying to predict probability of default. I use XGBoost. I got accuracy of 95%, which is fine. Great. But XGBoost, how does it work? Nobody understands. I mean, inside there is a lot of calculation and a lot of boosting of different trees that happen. So it's very complicated. But if using XAI, for example, SHAP, explain the fifth observation. How did you come up with the prediction of default or no default? This gives you a very nice waterfall kind of structure, which tells you how these x values of that observation has contributed to the final prediction, right? So look at this bottom. We have expectation of f of x, which is minus 3.3. This is the baseline prediction of log of odds. And then each feature, these are the feature values on the left hand side for that fifth observation, how they have contributed to the final prediction, which is 2.278. This is the log of odds, by the way. You can clearly see which variables are more, contributing more versus less. And then you can cross question, do these make sense? Economically speaking, are these in line with our experience, or are they intuitive? Okay, so this is just one of the ways explainable AI is helping to unbox the black box nature of machine learning. All right, going back to the slide. Materiality assessment is an important thing. How much rigorous your model validation should be, that depends on complexity and materiality, right? Materiality assessment talks about when you how complicated is the underlying mathematical infrastructure in your model. Plus, when the model drifts, you change the model. Okay, the coefficients get changed, or whatever features got changed. Are those material? So that we have to analyze. Okay, some model changes are just maintenance. So you change a few things here and there, which is not material, but some model changes could be material. For example, if you go from traditional approach to machine learning approach, that's a material change. Okay, so you have to document those and support that change through model validation. Model validation standards have to become more robust if the change is material. So that is there. In internal validation, you have to ensure stability and robustness of parameters. Again, all of these are general guidelines which intuitively make sense. It's nothing ridiculous or outside of the box. We're trying to blend human involvement, statistical understanding with the ML models, basically. That's the idea. Stability and robustness of parameters and all the hyperparameters that are selected, that has to be justified. Internal models. Data governance, a big topic, okay? Because we are using so much data from different sources, right? Structured, unstructured. We also have synthetic data, by the way. Remember, always we discussed, if you have, I'm talking 10 years ago, major challenge with LGD was lack of data. Lack of data was a major challenge. But today we are able to create synthetic data thanks to generative AI. Generative AI is being used to create artificial data, which simulates the real world behavior. Although it is not real, but it is simulated, but it is being used today to address that data lack of data issue. Okay, so whenever we use unstructured data or synthetic data, we have to reinforce on our data quality check, what kind of data we are introducing. That is part of data governance. There is also another angle, protection angle, so I missed that here. That is also very, very important. I'm not sure if you are aware of the regulation GDPR. So this is data protection regulation. That poses challenges with all of these. So GDPR has guidelines which are which goes like this. So I'll just highlight a few. You can only store or retain customer data that is necessary. All right. Second, there is something called as data minimization. You should not retain the data for longer than that is needed. Just you can only consume the data that is required for the model, not everything. There is also another rule which says customer has the right to be forgotten. If the customer wants to delete the data, then you have to delete the data. But with machine learning, see, all these state of the art latest machine learnings, they thrive on data, huge volumes of data. Okay. Now, with collection of a lot of data, we have to double check, are we violating GDPR rules? Okay, data protection, privacy, all these things come into picture. And yeah, and finally, model development phase. You have to ensure machine learning models are not underfitting and overfitting. Underfitting is not an issue because if it is machine learning, anyways, you are using a lot of parameters. So overfitting would be the main issue that you have to take care of. Replication. Lot of these machine learnings also use random numbers. Simulations, Monte Carlo simulations also use random numbers. Today we have a hybrid of everything. I mean, you can use, for example, there are Bayesian learning methods which use Monte Carlo simulation, MCMC, Monte Carlo Markov chain. Okay. So we use a lot of random numbers for simulation and for, let's say, random forest, where you are creating different trees by randomly dropping the features here and there, right? That's random forest. Replication means if you are asked to reproduce the result again, you have to store those random numbers in that correct order. So these are all the points highlighted in the paper, okay? I'm not making things up. You have to store those random numbers in the right order to be able to reproduce, okay? Because if you randomly initialize again, your end result will be very different. May not be very different, but it will not match with the original prediction. So these are some of the things that you have to take care of. So question from Sharavani, these checks are carried out for statistical models too, not only for ML model. That is correct, but you just have to put a lot of emphasis on these things. For example, overfitting, that's a major drawback of machine learning models. Everything that we do will have to do at with much more rigor and much more comprehensiveness. That's all we are saying. Okay, you are right. But with econometric models, because there is a lot of interpretability, it's very easy to do all these things. But with machine learning models, it becomes even more challenging and more involved to update this all of these infrastructures. Okay. All right. So to summarize, what can we do? What lies for us? So here's the thing. Uh, since we are risk professionals and we have to learn AI, do you all agree that this is high time that everybody should learn AI? Anybody wants to disagree? We are seeing what is happening in job market today. All of us are aware. Nobody is explicitly saying why there is a lot of layoffs happening, but we all know the reason. Do we all agree that AI is non-optional, something that everybody should learn? We all agree. Look at the top recommendation: adequate skill and expertise. Machine learning is going to get adopted. It is being adopted. It will only increase, it will not decrease. Look at the trend and look at the adoption. It is not, it is just, it's a reality we all have to accept, right? First recommendation is adequate skill and expertise. It is very important for risk professionals to understand machine learning because it is coming, and when it comes we should be ready. That is the skill that we need. Okay. And so ultimately we're looking at something which combines risk domain and AI. Now, if you want to understand AI, right, you don't want to understand, okay, how do we develop models to, that categorize pictures between cats versus dogs, right? So all these examples are there in machine learning. People use machine learning for biology, marketing, finance, everywhere. But for risk professionals, it's important for us to be aligned with the domain, which with what we are doing right now. Okay. Um, Risk and AI is a course that is offered by GARP today. And honest to God, this course is right now, it is perfect in terms of um, giving you the right blend of risk domain and AI flavor. Okay. So I'm also doing this course, by the way. So I've gone through the syllabus and I'm happy to say that I'm satisfied with the syllabus in the sense that it is up to date and it combines the right rigor in terms of quantitative and qualitative ideas that go into risk. It not only focuses on algorithms, right? It also touches upon some of the important dimensions that the regulators have spoken about. For example, ethics, fairness, bias, all these things are spoken in detail. So I personally find this course as very, very relevant today. So here are some of the points that I've highlighted. Why RAI is, I would recommend RAI to everyone. If you are into risk, then do RAI. Reason is first and foremost, it is conducted by GARP. We all know GARP is a reputed body, right? So that it has credibility to it. Instead of doing courses on Udemy and other things, right? If you do RAI, it adds a title to your profile and it complements your risk domain. Combines risk and AI, very important, right? Machine learning, if you look at, there are plenty of literature and videos available on machine learning. It is not something new. If you want to learn, you can learn, but are you able to apply those in risk? That is the question. So instead of learning generic machine learning, I would suggest learn AI and risk together, because it's important for us to remain, do justice to the area where we are working on. And instead of learning generic AI, we should learn something which is relevant for us. So combines risk and AI. And I like the syllabus. It has good rigor in terms of covering all the important algorithms, the math behind it. Not too much math is there in the course, but when we teach it, I ensure that all the mathematical results are derived. There is no black box, right? The main challenge with machine learning is black box. So when we teach it, we ensure there is no black box. But yeah, the course has nice blend. Let me actually quickly show you the syllabus here, just so that you get a feel of. So yeah, these are the modules that are part of the RAI exam. Tools, techniques, unsupervised learning, where we have principal components, cluster analysis, all those things. Supervised learning. See, there is a clear bifurcation. Supervised learning has an econometrics angle where you learn linear regression, logistic regression, linear discriminant analysis, which are heavy statistical probability theory based algorithms. Then we have ML based supervised learning, where we cover autoencoders, transformers, deep learning, neural networks, ANN, RNN, LSTM, all those things. Semi supervised learning, okay, partly labeled, partly unlabeled. Reinforcement learning, this is a very, very useful technique that actually impacts us today, okay. Autonomous driving, in finance you can think of algo trading. So there are agents which are doing trading on behalf of you using reinforcement learning. Model estimation, performance evaluation, natural language processing, NLP, generative AI, risks. So these are all pretty much introduction and quantitative side of things. Then comes risk and risk factors. So RAI does justice to this particular topic. It goes at length to explain what all risks are there in AI. Okay. Responsible and ethical AI, data and AI model governance. I find the syllabus extremely, extremely relevant for risk professionals today. Okay. So yeah, personally, I like the syllabus. It has a good coverage of everything. Um, so I would strongly encourage you to take a look at this course. It's just one time, one exam. Later on, I think it'll grow momentum and become bigger and bigger. But give it a shot. Look at the syllabus, and I would strongly recommend to do this course. It is highly relevant for our profession and for us to remain relevant and employable in this space, because I find these recommendations in sync, very much in sync with the syllabus. Okay, so this is highly, highly relevant. Now, just to wrap up, 5 more minutes. Why do RAI from peaks to tails? Okay, few pointers. So Peaks to Tails is the leader in risk and analytics training in India. Nobody even comes close when it comes to explaining topics with depth and originality. I don't think there is anybody who does it better than us. Build solid mathematical core with math primer. So here's the thing. One of the biggest challenges of understanding machine learning is that you need to have a very strong foundation. Okay, so if you go to Peaks to Tails and you go to RAI, there is a separate session on primers where I have explained all the basic mathematics that you need. Calculus, different functions, linear algebra, right? Statistical learning, regression. All of these things are required for you to understand machine learning. So these are covered. So this is to ensure that you have a strong mathematical core before you start. Excel and Python coverage. We have Python notebooks for all the different models. Python is not a very, I would say, how should I put it? There was a time when learning Python code was very, very essential. Today, I take it with a pinch of salt because if you ask ChatGPT, it generates the Python code in seconds. Okay, if you just ask, can you generate a Python code for reinforcement learning? Give some use case. It will generate that code very beautifully in seconds. So you can just take it, and if you have basic knowledge of Python to understand the code, you can read it yourself. You don't have to go hunt for Python codes here and there. Okay, so this is very easy to achieve today. Nobody explains the algorithms in Excel. Now, why we prefer Excel is everything is transparent. There is no black box, right? The whole purpose of this is to unbox the black box, right? Everything is explained in Excel using lot of animations that I have taken time over the last, let's say, 5 or 6 years to develop those animations. It's very important to have a geometric or graphical understanding along with the maths. And we do that in Excel so that you understand the algorithms in and out. Because let's be honest, I mean, running a Python code, for example, XGBoost, it takes 3 lines. You saw the Python code, right? It takes 3 lines to execute that package. Inside of that, there are so many rich ideas. Nobody talks about it. You should know them once at least to be confident that, hey, I know what is happening under the hood. And when you just run 3 lines of code, fit, transform, predict, that's it. It doesn't give you the feel of ownership, right? So we have gone to lengths to explain all these concepts using Excel. Let me flash some of the Excels that I have created so that you get an idea. So this is even neural networks. This is recurrent neural network, using this particular architecture to simulate a AR process. All the parameters are trained by hand. I mean, not by hand, by Excel solver, but you get in and out understanding of how the algorithms work. Forecasting GDP using recurrent neural network is done in Excel. Okay, and I have matched the results, closely matched the results with the Python code as well. To show a few more, when we talk about animation, right, it becomes difficult to understand concepts like PCA. But if so in PCA, what we do is we extract dimensions that explain the variability in the data. So this is one animation that shows you in what direction the variance is the highest. So you can see the green line explains, right now it explains 81.67% of variance. And this one explains 18.33% of the variance. So PCA works basically in a way where we try to extract the maximum variance. Which direction explains the maximum variance? That's our first principal component. So you can see this is the animation for PCA. Similarly, support vector machines. Not too complicated. Everybody talks about, so see, here's how it works. So there are two classes, right? Orange versus blue. You want to separate these two classes by passing a plane or highway, and you construct the highway in between them such that the width of the highway is highest. So in what direction you should construct the highway, and that becomes your decision boundary basically. For that, we have an animation. So you can see The nearest point, this orange and this blue, become the support vectors which hold the highway, and at different angles you get different width. So you stop where the highway is the widest, and then it shrinks again. Okay, so you maximize the width of the highway. This is support vector machine. Okay, as I said, I have done neural network in Excel as well. This is option pricing using artificial neural network in Excel. And you can see I have matched the Black-Scholes price, which is the this good stuff, right? S0 ND1 minus K to the minus, you know this, with the neural network prediction. And let me simulate. You can see 11, 11, 2 to 38, 38, they closely match. A very simple neural network architecture. You pass the S, K, R, tau, sigma, which are the option input variables, and then you get the option price. So we have tried to, unbox machine learning as much as possible using examples in Excel. And if you're familiar with my style of teaching, I try to derive everything with by hand. And also, one more animation I want to show you, maybe a couple more. Remember, we talked about ethics little bit. So ethics becomes a big issue. Regulators also have highlighted that when you use a lending algorithm, whether or not to give the loan to a particular person, you have to ensure that you are satisfying different uh, ethical requirements. For example, statistical parity. So between male and female, are you causing any discrimination? Or with age group, are you causing any discrimination? Right? These are protected characteristics. You cannot favor one particular group over the other. So these are big issues. If you do not satisfy this, companies will have reputational damage, which is highly costly. Right? So this shows you different ethical or biasness metrics. Mm, so in logistic regression, we have a threshold cutoff criteria, right? So you can see for various cutoffs, what are the different statistical parities or fairness measures, and then you can take a call, right? Equal opportunity, predictive power parity, and demographic parity. Okay, so that's there. And what else? Cluster analysis. Everybody talks about cluster analysis. This is an animation to show you how the cluster actually works. Let me actually close some of the Excel. There are too many Excels opened. Give me a second. So you understand the point, right? Where point I'm trying to make is three things. We have to learn AI, no questions asked. We have to learn AI with risk to be relevant. And third, you have to know you have to have the sufficient skill and expertise to understand the algorithms, not just how they work, right? So yeah, you can see this is a cluster analysis algorithm. How different points get assigned to different clusters, and then yeah, right now you can see there are or maybe after this one cluster and two clusters, and then they'll become one big cluster. So yeah, wherever possible, try to give animations. Pretty much we have animations for 80% of the algorithms. So that helps. And this is unique in the world. I don't think anybody has done all these things in Excel. Yep. So as I mentioned, Excel Python coverage includes derivation of key formulas, visual understanding. We have a large bank of MCQs that will help you to prepare for interviews and also pass the exam. And this is something that is ongoing. So if you enroll in the course, practical applications of ML in risk. So how are we using machine learning in risk use cases, right? Whether it is forecasting GDP or PD, LGD models, explainable AI, how are you using Gen AI? Gen AI is something that is rapidly transforming a risk landscape. So we'll learn the use cases of that as well. In fact, I am in the process of creating a chatbot which will answer all risk related questions, and it is based off of the knowledge that we have gathered over the years in peaks to tails. And the response will be very different from what ChatGPT gives you, because that is not a specialized um, tool which excels in risk or derivative, valuation area. So we are in the process of coming up with a chatbot on our own. And we'll learn the applications of GenAI, how GenAI is getting used to perform automated, let's say, loan approval process, or create model validation reports automatically. So all these practical applications will be part of this course. Um, right. So yeah, that's all I had for today. And this is the contact information. If you want to reach out, feel free to reach out. And yeah, the course is live for October if you want to enroll, or you can enroll for the next batch as well. It is 80% already recorded. Very recently I have recorded everything, so it's all new, it's all relevant, and this is the time to act. Okay, so that's all I had. For other follow-up questions in terms of pricing and logistics, reach out to us. All right, that's all I had. I hope you enjoyed this. It was more of an informative webinar, and actually a wake-up call for all of you to see the need to upscale ourselves, to learn AI in the context of risk. This is the right time, and we cannot wait anymore, because we know what is happening right now in the job world. So yeah, I invite all of you to learn AI and risk together. All right, thank you so much. Have a good rest of the day. Bye bye.